This time our t is going to be theta. This right here is a theta. Stop insulting me in the comments. Seriously, that's an absolutely disgusting letter, and I'm glad it died out 3,000 years ago with the Greeks, together with the Greeks. So yeah, this right here is way cooler. It's called var theta, curly theta, and as you might notice, it has theta in its name. Theta. Good morning, fellow mathematicians, welcome back to another video. Today we are going to calculate the arc length. We have talked about this on Wednesday, if I remember correctly, and the area of a cycloidal curve. So if you can't remember what a cycloid is, we have a plane right here. We are going to let a cute circle roll over it, and it's going to trace out this right here. Oh, this looks so beautiful once again. This is high-tier parametric curve drawing. And it's going to be quite easy actually. So this right here is just a simple, not closed curve, not a contour. We have those distinct endpoints right here. And it's also not a polar curve, so this makes things way easier. No double integrals this time and stuff like this. It's going to be really easy. And also we are talking about the arc length of one bump right here. You could say of one, if you draw a little nip right here, you're going to get the arc length of one mathematical titty right here. That's highly erotic, just like in my most favorite hentai. So we're going to go ahead and get started. If you remember correctly, this right here is our formula for the arc length of a parameterized equation. This time our t is going to be theta. This right here is a theta. Stop insulting me in the comments. I'm also looking at you, Fematica. You talked shit about me before, but now you're using this tool right here. No one wants to use this piece of crap anymore. This is so disgusting to write. Seriously, that's an absolutely disgusting letter, and I'm glad it died out 3,000 years ago with the Greeks, together with the Greeks. So yeah, this right here is way cooler. It's called var theta, curly theta, and as you might notice, it has theta in its name. Theta. So this right here is indeed a letter theta. Now leave me alone, you plebs. Yeah, okay. So we're not going to integrate with respect to t, we're going to integrate with respect to theta. Okay, so at first we have to find out what our endpoints are, our knots, you could say our notes. So we're going to start at 0 degrees angle rolled. No angle rolled right here at the moment, 0 degrees. So we are going to start with a lower bound of 0. But what's our upper bound? Well, this right here, our endpoint, T2, is going to be exactly 2 pi, because after a full rotation of our circle in this plane right here, we are going to get this cycloidal curve traced out. So our upper bound is 2 pi. And then integration of the square root of the x differentiated with respect to theta. Theta, indeed a theta squared, and then the same spiel with y. So if we differentiate our x, I'm going to just call it, yeah, I'm going to write it like this, not x naught. X dot. It really doesn't quite matter. So rho is just a constant. Let's bring it to the outside. Now we have to use the product rule. Theta differentiated with respect to theta is just 1. Minus, okay, sine differentiated with respect to theta is just going to be the cosine of theta. Okay, coolio. And the same spiel with y differentiated with respect to theta. Rho is a constant. 1 differentiated is going to give us 0. And negative cosine differentiated is going to give us, okay, cosine differentiates negative sine, so negative and negative is going to cancel out. So just sine of theta. This thing squared right here is going to give us rho squared. I'm going to put it like this. And then this chunk squared. That's just a binomial theorem. So this is 1, and then we're going to have plus cosine squared of theta. And then we are going to have negative 2 times the cosine of theta. Okay, I hope you agree with me. Also, this thing squared right here is going to give us just plus rho squared sine squared of theta. All of this has been in a square root integrated with respect to theta. So you see we have common factor of rho squared. So we can break up this third right here. One part is definitely strictly positive, that's the rho right here. So we can break this up into the square root of rho squared. Hey, that was a cool little break. So we have this chunk right here. We have rho squared as a common factor, it's positive, let's break up the third. Then we have the square root of rho squared, giving us the absolute value of rho. But rho is strictly positive, it's the radius. In our metric, in our Euclidean metric, it's going to be positive all the time. Meaning we are going to get this scalar rho, let's bring it to the outside, integral from 0 to 2 pi of the square root of. Okay, cosine squared and sine squared are going to give us 1 in the end. So 1 plus 1 is going to give us 2. Plus, no, it's negative, negative 2 times the cosine of theta. 2 is a common factor. We can actually bring it to the front. It's positive. We can break up the third into square root of 2 times 1 minus cosine of theta. We can bring the square root of 2 to the outside. Square root of 2 times rho times the integral from 0 to 2 pi of square root, I forgot my d theta, of 1 minus cosine of theta. D theta. You can probably integrate this in a different way than I do. I'm going to show it how I would like to do it. I'm going to put it here, it should fit. I hope you remember the double angle formula, namely that the cosine of 2 times a, in this case 2 times theta over 2 is nothing but the cosine squared of theta over 2 minus the sine squared of theta over 2. Okay, we can actually turn this around a little bit. Let me see, we need 1 minus the cosine of theta, so it would be good to get our cosine squared out of the way, meaning we have 1 minus 2 times sine squared of theta. Meaning we have the cosine of theta is nothing but 1 minus 2 times sine squared of theta over 2. And now we can just solve for our sine squared of theta over 2 by adding this on both sides, subtracting this cosine on both sides, and dividing both sides by 2 in the end. Meaning overall we have the square root of 2 times rho times an integral from 0 to 2 pi of the square root of, okay, we are going to have a factor of 1/2. This comes from dividing both sides by 2. Then we have, we are not going to divide it by 2, we are going to leave it as it is because we just have this factor of 1 minus cosine of theta. Meaning we are going to have 2 times sine squared of theta over 2, d theta. Now we have square root of 2 once again. Let's bring it to the outside, let's break up the third. Square root of 2 times square root of 2 is just going to give us 2. 2 times rho times an integral from 0 to 2 pi of, okay, square root of sine squared is going to give us the absolute value of sine on an interval from 0 to 2 pi, or rather from 0 to pi because we have theta over 2. Meaning it's going to be positive all the time. We are not going to get any negative values. No, we are not. So this is nothing but the sine of theta over 2 integrated with respect to theta. Integrating this is actually quite easy. So we have 2 times rho times 2 from this right here. Sine integrated is negative cosine. So we have negative 4 times rho, and then we have the cosine of theta over 2 from 0 to 2 pi. Cosine of 2 pi over 2 is the cosine of pi, giving us negative 1. So okay, this first part is negative 4 times rho. And then we are going to get negative 1. Okay, and cosine of 0 is nothing but 1. Okay, but we have this second part of integration, so negative 1. So this makes negative 2. Negative and negative is going to cancel out. This is good because it's an arc length. It's supposed to be positive. So we are going to get a times rho. And this should be right. I do hope so. After we have actually evaluated this arc length, we are going to take a look at the area next. So here goes. And I just decided for myself that I'm going to upload this version and then an uncut version. Where the uncut version is going to explain a little bit about the situation right here. So, yeah. We're going to calculate the area, and like I said, we are not dealing with a polar curve this time, meaning we are not going to deal with something weird where we don't really have a function anymore, like here, because for one x value we can have multiple y values. No, we don't have that, we just have this regular mathematical titty right here. Okay, how can we deal with this? Well, the basic idea right here is once again Riemann integration, meaning we are going to sum up infinitely many little rectangles right here. On this interval, our area is nothing but, well, integral from 0 to 2 pi. And how are our rectangles going to be constructed? Well, basically, they consist of a height, a y coordinate, times infinitely many, infinitesimally small x values, the x's. X times y is going to give us area of rectangles, infinitely many. That's the idea of an integral. Now I would like to introduce a little substitution, because we know what x actually is. X is nothing but this right here. If we differentiate this with respect to rho, with respect to theta, then this is nothing but, we have calculated this before, rho times 1 minus the cosine of theta, d theta. Regular substitution, you know how this works. And well, theta right here, this chunk right here is nothing but our y, meaning this is y times d theta. We can plug this chunk into here. Our region really doesn't change. Okay, so this up and lower boundary doesn't change. That's more of an informal substitution, you could say. Now we are going to get y squared integrated with respect to theta. Now we can actually plug this into here. Y squared, okay, we have this factor of rho squared right here. And then we have an integral running from 0 to 2 pi of this chunk squared, giving us 1 minus 2 times the cosine of theta, and then positive cosine squared of theta integrated with respect to theta. And we can actually break this up into 3 integrals. Meaning, we're going to get theta squared times an integral of 1 from 0 to 2 pi, giving us theta from 0 to 2 pi is nothing but 2 times pi. Then we have this next chunk, negative 2 times rho squared, integral from 0 to 2 pi of cosine of theta d theta. I'm going to show you a little visual way, because we're going to take a look at this curve right here. Okay, this is from 0 to pi. Then we are going to have from pi to 2 pi in this case. This area is positive and that's the negative counterpart. So those areas are going to cancel out. Same spiel here. People like visual stuff. This is going to be destroyed in the process. So by this visual proof right here, kind of, you can see that this goes to 0 actually. Plus rho squared times an integral from 0 to 2 pi of cosine squared of theta d theta. And you can use, once again, double angle formula. I'm going to do it using Phoenix integration, because why the hell not, just remembering the basics a little bit. Cosine squared of theta d theta from 0 to 2 pi. We need something to differentiate and something to integrate. We don't have many choices. Why not differentiate cosine and integrate the cosine? Differentiating the cosine leaves us with negative sine of theta. Integrating the cosine is going to give us sine of theta. This multiplied together and taking the integral of this chunk is going to leave us with, okay, we are going to get the cosine of theta, sine of theta from 0 to 2 pi. Minus and minus is going to be positive. Integral of sine squared of theta d theta from 0 to 2 pi. If we plug 2 pi into here, well, one of those is going to cancel out, namely on the sine. So this is 0, sine of 0 is 0. So this whole chunk is going to cancel out pretty nicely. Those two actually have the same area under the curve, so that's quite a cool fact. Otherwise, what we can do, we can turn this sine squared into 1 minus cosine squared using daddy fundamental theorem of trigonometry. Meaning we are going to get an integral from 0 to 2 pi of, well, d theta minus an integral from 0 to 2 pi of cosine squared of theta, d theta. And as you might notice, this and that is the same. We can add it on both sides to get 2 times this quantity is being equal to this chunk. We can divide both sides by 2 to get that our desired integral I right here that we wanted to get is nothing but, well, theta over 2 from 0 to 2 pi. It's going to give us just pi. Okay, this is our integral that we have right here. And well, you see we have rho squared times pi plus rho squared times 2 pi. It's nothing but, okay, rho squared is a common factor. Pi is a common factor. We have 2 plus 1 is going to give us 3 times rho squared times pi. And then we are done. So this is it. This is our area under this curve, exactly. And yeah, I hope you did enjoy this weird little video right here. I'm becoming way more improvised than the last time. Maybe you enjoy this kind of content. If you do, please tell me in the comments. Yeah, I thank you guys for watching. If you did enjoy this video, please like, subscribe, and recommend the channel. If you like, don't forget to support the channel in many different ways. Watch my, take a look at my Twitter subreddit. Buy those t-shirts I created. The fundamental theorem of engineering one is so good. I really adore this t-shirt. Also, you can support channel on Patreon whatsoever. No matter what you do, I thank you guys for watching, and up until the next video, have a flammable day. See ya. Should I go out to the right? Should I go out to the left? Something I haven't done in quite a while is taking something random from here. And let me see. Oh. Have a Cosmos Day. A Portal Wissen 2, 2018 day. Oh, that's actually not too old, to be honest. Oh, that's the one from Timo. The guy who's always running into the room. That's so amazing. Yeah, have a Cosmos Day, I guess. See ya.